Hello friends, we'll discuss in this video about the different types of reaction intermediates that we find in the organic chemistry. So when we write down the reaction, normally we write down the reactants and the products. But what we find during the reaction, that reactants never change directly into the products, right? They never change directly into the products. Rather, the reactants, they change first of all into some intermediate compounds, and those intermediate compounds then they change into products. These intermediate compounds are actually very unstable molecules, unstable species. The lifetime is very short, and the type of a product which is actually formed, it depends on the intermediate, what kind of intermediate we have. So in the organic chemistry, the study of the intermediates is very, very important, because finally the product that you get, it depends on the intermediate, right? It depends on the intermediate. Now let's take an example here. For example, if I have a reaction about the alcohols that change into the alkyl halides, like suppose we have a compound with the CH3 here and H here and OH, we have an ethanol. If you react this molecule with the hydrochloric acid, what we find that this molecule, it changes into the CH3 here, H here and chlorine here. So you get the alkyl halide plus you get the water. Now this is a substitution reaction. We know that hydroxide group is replaced by the chlorine, but the reaction, it doesn't change. Reactants do not directly change into the product. The alcohol directly does not change into the alkyl halide. Rather, we get an intermediate compound. During the course of reaction, we find from the alcohol, first of all, the hydroxide is lost here with the H plus sign. The mechanism we will discuss later on completely. The point here is that from the alcohols we get actually an intermediate here. We get an intermediate like this. When the hydroxide is lost from the carbon, so you get a carbon with the positive charge, right? You get a carbon with the positive. This is called as a carbocation. This intermediate is called as a carbocation. So carbocation is basically the intermediate where you find the carbon with positive charge. In organic chemistry, different kinds of intermediates actually are formed, right? So now this carbocation, this intermediate, then changes into the product. That is the final product that we get. So we'll discuss in this video, we'll discuss about the intermediate, correct? We'll discuss about the different types of intermediates. The kind of a product, as it said, that the kind of a product that you get depends on what kind of an intermediate we have. And all these intermediates, their lifetime is very, very short, right? They're highly unstable. Now, the different types of intermediates that we find in the organic chemistry is, one of them is a carbocation, right? Carbocation is a carbon with the positive charge. An intermediate where you find the carbon with the positive charge. This is a carbocation like this. Similarly, we can have a carbon with a negative charge. That's called as a carbanion. That is the carbon with the negative charge. We can have another intermediate. We have another intermediate, the free radicals, right? Free radicals, right? So carbon with one or electron, right? Okay. So we have another intermediate, carbenes. We have a carbene, right? We'll discuss about all these intermediates one by one. Now let's start with the first intermediate here, the carbocation, right? Carbocation is basically, it's a carbon with a positive charge, and therefore we find that the carbon has 6 electrons in the valence shell. And how is it formed? For example, you can get the carbocation like this. Suppose we have here the different alkyl groups here attached with the carbon, and if suppose here you get an atom A attached with the carbon, and the bond breaking occurs such that both electrons, they go with the atom A, and what you get the carbon with the positive charge. Now when A atom is lost as A negative here, you remove the A as A negative, heterolytic bond fission occurs here, and you get the carbocation, you get the carbon with the positive charge. Now you have only 6 electrons in the valence shell. So carbocation has 6 electrons in the valence shell. That means it is actually electron deficient, isn't it? So this is an electron deficient species. And what is the structure? The structure, very simple, it's a trigonal planar. The structure is trigonal planar. That means the carbon is having the sp2 hybridization, because when you have sp2 hybridization, only then you can have a trigonal planar shape. So these are the 3 groups which are attached with the alkyl, with the carbocation, and this unhybridized p orbital, which is empty actually, it is the orbital which remains above and below the plane. So these are the 3 R groups attached to it. So the structure is trigonal planar. Hybridization here is sp2. Now let's discuss about the different types of carbocations, right? We can classify the carbocations into primary, secondary, tertiary. Depends on what, how many alkyl groups are attached to the carbocation. If you have a carbocation which is having 3 alkyl groups, right? It can be methyl, it can be anything. If there are 3 alkyl groups attached to the carbocation, that's called as a tertiary or a 3-degree carbocation. If there are only 2 alkyl groups, we call it as a secondary carbocation, right? If only 1 alkyl group is there, that's a primary carbocation. If there's no, we call it as if there's no alkyl group, then this is a methyl carbocation. Now what is the stability order of these different types of carbocations? Which is more stable? Do they have any difference in the stability? Yes, there is a difference in the stability, and we can talk about their stabilities, right? So if you want to study the stability of the carbocations, we can explain the stability of the different types of carbocations with the 3 different concepts, right? So these 3 important concepts: inductive effect, hyperconjugation, and resonance. These are the 3 important effects that tell us about the stability of the carbocation. We can actually compare the stability of the different types of carbocations with the help of inductive effect, with the help of hyperconjugation, and also with the resonance, right? So we'll discuss how we can get the stability of the different types of carbocations from these effects. Let's suppose we have a tertiary carbocation, and we know that in a tertiary carbocation there are 3 alkyl groups, and for a secondary carbocation there are only 2 alkyl groups, and for a primary there is only 1 carbocation, right? So what will be the stability order? Do they have any difference? Yes, they have. We know that this carbocation, which is electron deficient, right? It's electron deficient, and the alkyl groups, these alkyl groups, they have the positive inductive effect, right? They have the plus I effect. They have the plus I effect, plus inductive effect. That means they are donating the electrons. They can donate the electrons, right? So this electron pair, it will be slightly closer from this side as well. So you have 3 alkyl groups which are donating electrons to the carbocation in the tertiary one, while at the secondary one it has got only 2 carbocations, right? It has got 2 electron donors, right? So you can see here 2 groups. Hydrogen, does not donate the carbon to the hydrogen. Hydrogen does not donate the electrons to the carbocation, right? So you find here only 2 electron donating groups in the secondary. For the primary, it's only having a 1 electron donor group, right? So these are the electron donating groups because they have the plus I effect. Obviously the tertiary one will be more stable, isn't it? And then the secondary, then the primary. Why? Because in tertiary there are 3 electron donating groups, and they will decrease the the deficiency of the positive charge, right? Deficiency of a electron deficiency will be decreased in the tertiary, then secondary, then the primary, because we have electron donating groups here, right? So therefore the order will be in this fashion. So that means the tertiary carbocation is more stable than secondary, then primary, and the last one, the methyl carbocation, it does not have, it will be the least one, right? So therefore we can say this is the tertiary is more stable, then secondary, then 1 degree, and this is the methyl carbocation, or we also call it 0 degree, right? Or the methyl carbocation. So the order will be like this, isn't it? So which means that the carbocation, right? A carbocation is stabilized if you attach an electron donating group, right? So if you attach any electron donating group, a group which can donate electrons to the carbocation, it will increase the stability. Why? Because carbocation itself is electron deficient, and any group which can donate electrons to the carbocation will be more stable, right? But if you attach electron withdrawing group, a group which can withdraw electrons, right, that will make it unstable, right? So suppose we attach a group to the carbocation which can withdraw electrons, right? You know, any group which has a negative I effect, okay, which has a negative inductive effect, that will decrease the stability, that will make it unstable. Electron donating groups stabilize the carbocation, electron withdrawing groups, right, electron withdrawing groups, it will make it unstable, right? So this is actually the stability with the help of inductive effect. We can also explain the stability order of the different types of carbocations with the help of hyperconjugation, right? Hyperconjugation also explains the stability order, why the tertiary is more stable than secondary than primary, right? We know in the hyperconjugation, we have studied in the previous video what the hyperconjugation means and how, you know, we can draw the different structures, right, canonical structures through the hyperconjugation concept. Okay, we know that hyperconjugation, it also stabilizes the carbocation. Let us discuss here. For example, we have a carbocation here, and this carbon hydrogen bond over here, it will break and it will shift over here, and you get a double bond between the carbocation, and the positive charge is on the hydrogen. And then in next structure, what will happen? Again, this particular hydrogen, right, okay, it will shift over here, and you can get another structure like this. You get a positive charge over this hydrogen, and then the third structure. From this one, again one more structure like this, electron pair. From this one, it will shift here, and you get a bond here, double bond is here, CH2, and then the hydrogen with the positive charge, right? And then again it will go back, and you get the first one. Now the positive charge on the carbocation, it gets delocalized over the alpha hydrogen atoms, right? We know that for the hyperconjugation, the most important requirement is that we should have an alpha hydrogen atom. Only then the hyperconjugation is possible, right? So over here, higher the number of alpha hydrogen atoms, more will be the stability, isn't it? So you find here the 3 alpha hydrogen atoms, right? For this particular carbocation, there are 3 alpha hydrogen atoms, and we got how many structures? Okay, we got a total 4, right? So 3 plus 1, that means the number of alpha hydrogen atoms. So plus 1 plus the 1 itself. So that total number of hydrogen atoms is 4. Sorry, the total number of alpha hydrogen atoms is 3, and the total number of the structures here you get from the hyperconjugation is 4, right? So therefore, if you get in the primary one, in the 1 degree carbocation, you get the 4 structures, 4 canonical structures, right? So how many alpha hydrogen atoms are there in the secondary carbocation? In the secondary, there are 3 alpha hydrogen atoms here and 3 alpha hydrogen atoms here, and plus the 1 itself. So total number of structures that we can draw for the secondary, it will be, I think, 7, right? So for this one, you will get 7 canonical structures, right? For the primary one, you got 4 canonical structures, right? Because we have 3 alpha hydrogen atoms, right? We have 3 alpha hydrogen atoms, right? 3 alpha hydrogen atoms are there. So the total number of canonical structures is 3 plus 1, okay, that is 4. Here we have actually 6 alpha hydrogen atoms, so 6 plus 1 is 7, right? In the tertiary one, we find how many? 1, 2, 3, right? So 3 groups are there, each having 3 alpha hydrogen atoms. So total number of alpha hydrogen atoms is 9, and 9 plus 1 means 10 canonical structures, right? 10 hyperconjugate structures can be drawn, right? So that is why the tertiary is more stable than secondary than primary, right? So we can explain, that means we can explain the stability order of the carbocations with the help of hyperconjugation as well, right? Okay, we discussed the stability order of the carbocations with the help of inductive effect, and now with the help of hyperconjugation. So both the concept, they tell us that, what they tell us? They tell us that tertiary is more stable than secondary than primary, right? Okay, so the conclusion is same, an explanation from the different perspectives. Okay, now we can explain the stability of carbocations also with the resonance, right? So resonance also helps us to understand the stability of a carbocation. See, if you have a carbocation, and if that particular carbocation is always on that carbon, this is called as a localized carbocation, right? However, if you can delocalize this, if you can delocalize the positive charge, that is a resonance, right? That is the resonance. So that the delocalized carbocation is actually more stable. And how we do it? For example, we have a carbocation over here, and we have a single bond, then a double bond. In resonance, when in the resonance video, you can just go back to that and just see what are the conditions for the resonance, and can this carbocation be delocalized? Yes, it can be. Why? Because it is actually in conjugation with a double bond, right? We have a carbocation, then a single bond, then a double bond. So this is the carbocation is actually at the allylic position. So this carbocation can be delocalized. This electron pair will shift in this direction, and it will go towards the carbocation. The pi bond will break, and it will go towards in the direction of a carbocation, and you get another canonical structure like this. You get this carbon with the positive charge now, and the double bond will shift over here, right? Now, due to the delocalization, initially it was here, the carbocation was here, now it is delocalized over this particular carbon. Now the second canonical structure, it will go back to the first one, right? It will go back to the first one. So these two canonical structures, they make it stable, right? They make this positive charge stable. Higher the delocalization, if you have a carbocation which can be delocalized, that provides stability. So more the delocalization, that means more will be the stability, correct? So that is why allylic carbocations are much more stable than the one why you do not, you cannot delocalize. That means this allylic carbocation is more stable than this carbocation. Let me take an example here: CH3, CH2, and the CH2 positive charge, right? See, this one is 1 degree carbocation, this one is also 1 degree carbocation, correct? So both are 1 degree, but what is the difference? The difference here is in the allylic carbocation we have a double bond, and because of the double bond it gets resonance, right? It gets delocalized, and that provides stability. While as this particular carbocation over here, right, this particular carbocation over here cannot be delocalized because there is no double bond, so it will always be there with the positive charge. So that's why the allylic carbocation is more stable than the non-allylic one, right? And higher the delocalization, that means if you can draw more canonical structures, more resonance, that means more stability. Like in the benzyl carbocation, right? The benzyl carbocation is highly unstable. If you attach a phenyl ring to the carbocation, that provides a lot of stability to the molecule, to the carbocation, to the intermediate. Why? Because we have 3 double bonds here, right? There are 3 double bonds, and this positive charge, it can be delocalized over the ortho position, the para position, and the ortho position. Let me draw the structures, how we can draw the structure, how we can draw the different canonical structures. For example, we have a carbocation like this. We have a positive charge over here, and then you have a double bond here, a double bond, one more double bond here and here, right? And you see the positive charge, then a single, then another double bond, single, double. So this is whole system is a conjugate system, right? This is a conjugate system, and therefore you can delocalize it. The pi bonds from the ring, they shift towards the carbocation, and what you get another structure with the double bond over here, and the positive charge will be or the ortho position, and you get the second structure from this one, right? So this is the first canonical structure. Now this is the second canonical structure, right? And you can change this second structure back into the third one, right? You can change it, you can delocalize over here. This pi bond breaks and it forms between these 2 carbon atoms. Right now the double bond breaks here and it goes over here, and therefore the next canonical structure that we can draw will be like this. You have a double bond over here, the para position is having the positive charge, and the double bonds over here, right? So this is the third canonical structure, and you get the third canonical structure from from the second one, right? From the second one, right? Okay, from this one. Now you got at the ortho. Now at the para position, again we can delocalize it further, right? We can delocalize it further, and you can just shift it in this direction, okay, so that you get the positive charge over the ortho position, this ortho position. Now you get a double bond over here, here, and here, right? And then what will happen? Again, the fourth structure, this fourth structure, we can change it into the first one. How is that possible? If you push these electrons over here, right, you get a double bond between these two carbon atoms, right, and therefore you get the first one back, right? This is, so how many structures we got? 1, 2, 3, 4, right? So that means very much stability. And the benzene ring actually that we attach here, that's an aromatic compound, right? So that makes the carbocation highly unstable. That is why benzyl carbocations are even more stable than allyl carbocations, right? Okay, benzyl carbocations are very much stable than allyl carbocations, right? So because we have more number of canonical structures in the benzene than the allyl, right? So that's why it is more stable. So higher the number of rings, say if you attach the more benzene rings to the carbocation, that will provide more stability to the carbocation, right? Okay, now finally what we can get the conclusion. The conclusion here is that the benzyl, right, if you attach a carbocation, that is more stable than allyl, which is more stable than the tertiary, then secondary, then primary, and then the methyl carbocations, correct? Because you find here the resonance, here you find also the resonance, while the benzyl one provides extra more stability because of the higher number of canonical structures, and because the benzene ring is also aromatic, and we know that aromatic compounds are much more stable, right? That's why the benzene, once you attach a benzene to the carbocation, it provides a lot of stability, right? And over here, you know, this is more stable. Why? Because there is resonance, right? And in all these carbocations there is no resonance, okay, in the tertiary, secondary, and primary, right? And the order is tertiary, secondary, primary, and this is the final order, right? This is the decreasing order. This should be the decreasing order of the stability, right? So that means, you know, benzene provides stability, and if you attach more number of benzene rings, you know, to the carbocation, that will provide more stability. So that means greater the number of benzene rings, more will be the stability of the carbocation. Now let's do some exercises, right? Let's do some exercise. Let's use this concept what we studied and to find out the stability order of the different molecules. You see here we have a carbocation, and then we have a single, double, single, double. So whole system is under resonance, this is under conjugate, right? This is a conjugate system, and therefore you can delocalize the positive charge, right? We can, I think, delocalize like this, isn't it? So I can draw another structure for this molecule. The double bond will be here, and the positive charge will be here, right? Okay, and another double bond is here, right? So this is the second canonical structure. This is the first structure, and this is the second structure. Okay, this is the second canonical structure here. And again you can draw another canonical structure from this one. How is that possible? The possible is, you know, if you push it over here and you get a positive charge over this position, right? Now you get a double bond here, and the double bond is here. So you got the three structures here, right? These are the three canonical structures. Clear? This is how, you know, the positive charge is delocalized. Okay, now let's talk about this molecule. Can we delocalize this positive charge? Can we delocalize? Just have a look at it. We have a positive charge, then a single, and again a single, then a double bond. So that means this molecule, it cannot be delocalized. No resonance is possible here. Why? Because it's not the conjugate one, isn't it? We have two single bonds. We don't have a alternate bond, right? You need to have a positive charge, then a single, and then a double bond. You know, this double bond should be here, right? Isn't it? It should be here, but it's here. You got the two single bonds. So this is not a conjugate system. That's why there is no resonance possible in this molecule, right? There's no resonance in this possible. No resonance is possible here. No delocalization is possible here, right? Now let's take another case. Can you delocalize this molecule, this carbocation? Yes, we can delocalize. Okay, just have a look at it, right? You can delocalize because we have a carbon with a positive charge, then a single bond, then a double bond. That means you can draw the structure, right? You can draw the structure. But there's one more thing also. See, we have an oxygen with a lone pair of electrons, right? And we know that if lone pair of electron is there, it can also be delocalized, correct? We got a positive charge then a single bond, then a lone pair, right? Okay, so resonance is possible over here, isn't it? So we can draw the two more resonating structures and they will be slightly different, right? Suppose here if I draw the double bond in this direction, isn't it? So what you get? You get a double bond over here, okay, and therefore the positive charge will be here, right? If this is the first structure and this will be the another structure, right? This is another structure, another canonical structure. Or if the resonance occurs from this direction, if the resonance occurs from this direction, the lone pair, it starts forming a bond with this, okay, it starts forming a bond with this. What you get then? You get a double bond over here, isn't it? And the positive charge will be on the oxygen, right? But the three, if you look at the three canonical structures, they are not equivalent, right? They are not equivalent. The third one will be, the least stable, right? Among the canonical structures, there is the difference in the stability, right? The third one is the least stable. Why? Because we have an oxygen, which is an electronegative element. Oxygen, an electronegative element with the positive charge that is relatively unstable, okay? The carbon with the positive charge is not so unstable as the oxygen with a positive charge, right? So that's why you get the three canonical structures here, but there is some difference, okay? These are the three structures that we can draw here, correct? These are the three structures we can draw, but there is some energy difference, okay? The least stable one should be the third one, okay? The least stable one is the third one here. Among these three, right here, you can see the first one and the third one, right? They almost have the same energy, correct? The first one and the second one, they almost have this, the same stability, correct? Energy is same, stability is same. So first one in terms of energy will be equivalent to the third one, but the second one is more, it is more stable. Why? Because you got here a secondary carbocation. Here this is a secondary carbocation. Here we have a primary. Here we have a primary. So these two are same or almost equivalent, right? The first and the second, the first and the third one, they are the equivalent, but the second one is little bit more stable, right? So there can be some stability difference among the canonical structures. That's what we have studied in the resonance, that the resonating structures, they may be equivalent or non-equivalent, right? You can refer to that video to find what does it mean and how do we find the equivalent and non-equivalent resonating structures. So I suggest if you still have some doubts in those in this concept, right, just go back to the video where we discuss the equivalent and non-equivalent canonical structures, resonating structures. So go back to the resonance and just replay the video again. Fine. So let's take another example here. Which among the two, right, is more stable? Which among the two is more stable, right? Here the most stable, is first one, right, and the second one. Why? Why is more stable? Because there is resonance. You can find that here in this carbocation, it can undergo resonance, and you can draw a canonical structure like this: CH2 single bond CH. A double bond will be now over here, and therefore you get a positive charge at this point, and there is no resonance here, right? There is no resonance here. So resonance effect is actually a dominant effect, correct? Resonance effect is dominant over the inductive effect. No doubt this is a secondary, right? This is a secondary carbocation. This is a 2-degree carbocation. This is a primary carbocation. But here this primary one, it actually undergoes resonance. So it has a double bond. So the positive charge delocalizes, while there is no delocalization or the resonance in this molecule. So that's why the first one is more stable. So we can say the first one is more stable than the second one, right? Okay, that is the order of stability. Now let's talk about the stability of these three. Now see, this is the tertiary carbocation, this again is the tertiary carbocation, this again is the tertiary carbocation. All of them are tertiary, right? So that's not a problem, right? So inductive effect cannot help us, right? Okay, so what's the difference now? The difference here is that we got a benzene ring here, okay, and we got here the two benzene rings, okay. Here we do not find anyone, right? Only the methyl groups are there. We have only the CH3 here, right? This is a CH3, we know. This is another CH3 group. This is another CH3 group. There are only 3 methyl groups. So obviously the benzene ring provides more stability. So for this molecule, for the third one here, it has 2 benzene rings, and one benzene ring provides the positive charge. This positive charge can delocalize over here when we draw the resonating structures here and here, right? So these are the 3. here also the resonance, right? Here also the positive charge, here also the positive charge, correct? So this positive charge, that we find at this carbon, it can be delocalized over all these positions, correct? Okay, these are the canonical structures that we can draw. Okay, we can draw. So how many canonical structures will be there? There will be the 7 canonical structures for this one, right? Okay, 7 resonating structures will be possible for the third one. And for this first one, how many resonating structures? You got, or you can delocalize this positive charge over the ortho position, at the para position, and again at the ortho position. So 3 plus 1, that is 4, correct? So 4 resonating structures, and there's no resonance over here. That's why the more the stable, more the resonating structures, more will be the stability. So that's why the third one is more stable than the first one, which is more stable than the second one, correct? This should be the order of stability. Third is more stable than first than the second, right? Let's take another example here. Now, which among the two is more stable? See, this one is secondary, okay, this one is also secondary, okay, both are secondary carbocations, and there is no resonance in anyone, right? There is no resonance. So how do we explain it? You find, see, from this side it has a one, if you look at this particular carbocation here, it has a methyl group, here it also the methyl group, so the one group is same. Now what we find over here, this is actually a propyl group, a 3 carbon alkyl group, isn't it? This is a 3 carbon alkyl group, this is C3, right? Okay, alkyl group, this is an alkyl with a 3 carbon, right? So C3 molecule, right? Over here also this is a C3 molecule, right? And we know, if the number of carbon atoms is more in the alkyl, the inductive effect is more, correct? More the number of carbon atoms, more will be the inductive effect. But here the number of carbon atoms is same. Then how do we find it? So which is more electron donating, right? It has a methyl which is electron donating. This also has a methyl. Okay, this also has a alkyl group, right? Okay, this also has alkyl group, a C3 carbon. Number of carbon atoms here, this is alkyl with the C3. Okay, that is same. But what is the difference? What you find the difference? The difference is structure. This is a linear molecule and this is a branch, right? Okay, this is a branch, and higher the branching, more will be the inductive effect, correct? Higher the branching, more is the inductive effect. That means the isopropyl group actually has a higher inductive effect, right? This group actually has a more inductive effect than the normal propyl group, correct? Okay, this has a higher inductive effect. The inductive effect order is like this. Okay, the positive I effect for the isopropyl is more than the normal propyl, correct? This also has a positive I effect, but the order is like this. So that is why this one, the first one, is more stable than the second one, and therefore I can say the order of stability should be 1 degrees. The first one is more stable than the second, isn't it? That is the decreasing order of the stability. This should be the answer here, right? Okay,